Okay, section 19.5, spontaneity of redox reactions under conditions other than standard state here. So let's consider a redox reaction, a generic form, A plus B. I'm sorry, this is a B. This is a plus. In equilibrium with C and D. And if you recall, the free energy change for non-standard conditions, so conditions other than standard, the free energy change is the standard free energy change plus a correction factor, RT ln Q, right? Okay, so we're going to use that here. Now let's imagine that we want to take this relationship, delta G, is minus NFE, and delta G naught is minus NFE under standard conditions, right? We can substitute those in here. So now we have minus NFE, this is going to be E cell, equals minus NFE cell standard, right? Plus RT ln Q, right? Just substituting those in. So now notice that both terms have minus NF in them. So what if we divide everything by minus NF? We'll get E cell, right, equals E standard cell minus RT over NF ln Q, right? We've actually looked at that in the previous section, this RT over NF ln Q, and what we found was that we could take R at 298 Kelvin, divide, so R times T, and divide that by F, and then change the base from natural log, or base E, to base 10, which would be log. And we find that the cell potential in this case would be the standard cell potential minus 0.0592. I won't put V for volts here, but it's in the unit of volts, divided by N, number of moles of electrons transferred, times the log base 10 of the reaction quotient, right? Okay, and there we go. There's our result right there. Now this is an interesting result. Essentially what it says, I'm going to erase this down here and write that a little bit more clearly. What this says is that if we're under non-standard conditions, okay, so in other words, the concentration of a solute that's involved in the chemical reaction is not equal to 1 molar, or the pressure of a reactant or product is not equal to 1 atmosphere. Those are non-standard conditions. We can calculate the cell potential under those conditions just by using this equation here. The standard cell potential minus 0.0592 over N times the log base 10 of Q. Okay? It's a useful equation. It's actually, it has a name. It's so useful. It's called the Nernst equation. So not all the equations that we use in this course in chemistry have names, but this one actually does. It's called the Nernst equation. It's a very useful equation. So now let's take a look at just a brief little example of how we use it. Let's say that we have a reaction, zinc reacting with copper 2, and that forms zinc 2 aqueous plus copper. Okay? So let's say that we're at 25 degrees C, and we have certain concentrations. So let's pick a couple of concentrations here just to take a look at what we might get. Let's say, for example, concentration of copper 2 is 0.1 molar, and the concentration of zinc 2 is 0.001 molar, right? I'm just picking some easy numbers to deal with just so we can look at. And let's say we want to calculate each cell. Well, the standard cell potential, that's easy enough to do. We've done that in a previous example. That's the cathode standard cell potential minus the anode cell potential. And for this one, if we look up copper, it's 0.34 volts. And if we look up zinc, it's minus 0.76 volts. We did that at the beginning of this chapter, and you get 1.10 volts. So there's our standard cell potential. But now, can we calculate the cell potential by using the Nernst equation? Well, we would take the standard cell potential, and we would subtract from that 0.0592 over n times the log of Q. And what we're going to do in this example, we now know this is 1.10, and this is 0.0592, is we're going to divide it by n and then multiply it by the log of Q. So let's figure out what n is. N's easy, it's 2, and here's why. If you look up the standard reduction potentials for these two substances, 2, there's your n equals 2. And then the zinc is the same thing, it's 2 also. Right? So if they're the same number in the two equations that you're looking at, then that's going to be n. Right? It's the lowest common factor or multiple of them, so 2 would work. So that's a 2. Now we just need to figure out what Q is. Q, remember, this is a solid, so that's not going to be in the expression. So it's zinc 2 over copper 2. So concentration of zinc over concentration of copper, right? The ions, because they're aqueous. So in this particular problem, it looks like the zinc is 0.001 molar, right? And then the copper is 0.1, right? 0.1. Again, I picked these numbers for a reason. The math is easy, right? 0.001 over 0.1 is 0.01. Okay? And so now here's what happens. If we try to find out what log of Q is, that would be the log of 0.01, and that would be minus 2.0, right? You can do that on your calculator. Here, I'll show you. 0.01 log, 0.01 log is negative 2, okay? So that's negative 2. That's not bad. So now, here's what we do. We come back and we use this equation here. But now we know this is, 0.01. So now that's equal to 1.10 volts minus 0.0592 over 2 times negative 2, right? A log of 0.01 is negative 2. So look what happens. Again, I picked easy numbers. I want these two to cancel. And then you got minus some minus, that's a plus. So it's 1.10 volts. 1.10 volts plus 0.0592. Right? Because you're subtracting a negative and the 2's there cancel. So it's just 0.0592. So now it's going to become 1.1592 volts. That's too many sig figs, obviously. 1.16 volts perhaps. Okay? So now the cell potential is greater than the standard cell potential. The standard cell potential was 1.10 volts. Spontaneous reaction, right? As written. But because Q is less than 1, that means that we don't have as much products as we need, right? Q is less than K. So the reaction is going to proceed to the right, which means you're going to get more. So that shows up in the cell potential. The more spontaneous the reaction is, the higher the cell potential. So in this case, we get 1.16 volts. It's kind of a cool application of this Nernst equation. And so we can use that in terms of what we call concentration cells. And so a concentration cell is a galvanic cell where you have the same reaction in each container, but different concentrations. So what I mean by that is you would take 2 beakers, for example, put a piece of zinc in both, right? So I'm going to take a piece of zinc. So this is zinc. That's a zinc electrode. And then I'm going to put the same metal, right? What's the deal? How can you do this? How can you have the same metal? Don't you have to have 2 different metals so that you get a cell potential? Well, that's true. The standard cell potential is the cathode reduction potential minus the anode reduction potential, but those under standard conditions. So what happens is, if this is a concentration, let's say, of 0.1 molar, and this is a concentration of 1 molar zinc ions, of course they're aqueous, right? We're dissolving them in water. And then we measure the voltage. So you have a voltmeter here. Okay? Now, here's what happens. Of course, you have to have a salt bridge, right? This is not going to function properly without a salt bridge. We learned about that early in this chapter. But here's what happens. It turns out if you set this up, your voltmeter will give you a cell potential of 0.0296 volts. Sorry, I almost said molar there. And the reason is, this ends up being the cathode. So it's positive, and this one ends up being the anode, and that's negative. The reason you get this cell potential is because the difference in the concentrations, right? So what happens is Q is equal to the concentration of the zinc 2 in the anode divided by the concentration of zinc in the cathode. So Q then would be in the anode 0.1, and then in the cathode 1.0. So you get 0.1, right? That ratio is 0.1. Log of Q would be the log of 0.1, which is minus 1, right? So you actually have a negative 1 there. So come back to this equation here. I'm going to come back all the way to this one up here. The Nernst equation, right? N is 2, right? So we know that's 2. We have the 0.0592. But now we're going to have a negative 1 in there, right? We just calculated that that's negative 1. So minus a minus 1. This is 0, right? That one's 0 because there isn't any difference in potential between zinc and zinc if they're at the same concentration. However, even though that term, the standard cell potential, is 0, we're still going to have a term here because N is 2 and log of Q is negative 1, right? So differing the concentrations of the same metal ion, even though it's the same metal, that difference in concentration will result in a cell potential. All right? It's 0 minus 0.0592 over 2 times minus 1. Well, that's 0.0592 over 2, right? Minus a minus. So it's not real big. And usually these cell potentials in concentration cells are very small. You see why they call it a concentration cell? We're essentially measuring the potential due to a difference in concentration. There's an energy associated with that, which we'll call the cell potential due to that difference in concentration. That's a result of this idea of the Nernst equation, which says that the cell potential, not only does it depend on the standard cell potential, it also depends on the value of Q and what those concentrations are. So hence, concentration cell. Now I want to show you, just really briefly for that particular concentration cell, how we would do line notation. So when we do line notation, we put the anode on the left, and we do the cathode on the right. Okay, so the cathode goes over on the right. Now, I've always struggled memorizing these sorts of notations, but here's how I remember it. Reduction. Reduction starts with an R, and so does right. And we remembered that cathode starts with a consonant, and right starts with, or reduction starts with a consonant. So that's the way to do it. We put the solid on the outside. So you put the metal on the outside. Then you have a line. You're working your way inward. Then you put the ion, the aqueous ion. But in a concentration cell, you also indicate what the concentration is of that particular ion. So in the anode here, the zinc was 0.1 molar. Then you do the salt bridge, and then you do the same thing on the other side. But this one was 1 molar. Okay? So again, the idea here is that this is what we call a phase change. And then this is the salt bridge. So the argument here is that on the left side you got the anode, there's the metal. There's the metal ion. The metal ion is in water. That's a different phase of matter than a solid. So we put a line, a vertical line there. Then we have the salt bridge, and then the salt bridge is connected to the other electrode through the solution, right? There's the metal ion. And because this is a concentration cell, we're going to indicate the concentrations. And then again, you got the other metal. So for the concentration cell, the metal is going to be the same. If we were doing this for a different type of galvanic cell, so maybe one that has two different metals, copper and zinc, then we would have the symbols for the two different metals there. We can also use this actually to figure out the value of equilibrium constants. It's kind of cool as well. It's a nice little technique.